This video will cover Chapter 6 out of the Gabrosek Stephenson textbook. Chapter 6 is about bivariate data, where we have one categorical variable and one quantitative variable, and more specifically, our quantitative variable broken down into different categories based off of a categorical variable. The first type of graph that we can use if we have this type of data is comparative box plots. Here we have height broken down by class standing. Please note that SPSS does not recognize when variables are ordinal, so it does go freshman, junior, senior, sophomore, rather than freshman, sophomore, junior, senior. So the question, does there appear to be a strong relationship between class standing and height? And then explain. And there does not appear to be a strong relationship. The reason why, all the maximums are roughly the same, Q3 is roughly the same, the medians are roughly the same, Q1 is roughly the same. Really, the only main difference between any of these is I haven't had any really short freshmen in any of my classes. And this should make sense. By the time that you reach college, you are pretty much done growing. So it's not like we can walk down the hallway and be like, oh, you're 6'2", you must be a junior, or anything like that. How tall you are is probably not impacted whatsoever based off of what your class standing is. The other type of graph that we can use is comparative histograms, where we've got a histogram, a separate histogram for each one of our outputs on our categorical variable. Here we've got number of shoes broken down by your gender. And in the data, I've only had males and females. So here we can see the number of shoes for females on top and males on bottom. And does there appear to be a relationship between gender and number of shoes? And absolutely. Basically, any number to describe females is going to be higher than the same number used to describe males, or the same output used to describe males. The minimum, the maximum, Q1, Q3, the median, the mean, the range, the standard deviation, the variance, all of these values are higher for females than they are for males. The maximum for males is about 42. There are plenty of females that have more than 42 pairs of shoes. The mode for females is around 20. The vast majority of males have less shoes than that. So there is a strong relationship. If I tell you someone's gender, that changes, that impacts how many shoes they likely own. Besides our two graphs, all of the other descriptive statistics we talked about in Chapter 3 are mean, median, Q1, standard deviation, variance, range, minimum, maximum, IQR, all of those things we can find broken down into categories as well. We can find the average number of shoes for males. We can find Q3 for height for juniors. We can find all these numbers for our quantitative variable, only looking within one of our outputs for our categorical variable. Moving right along to our statistical inference, there is another sampling distribution that exists, and that allows us to do our confidence intervals and our hypothesis test, but we won't talk about what it looks like. So our hypothesis test, same 5 steps as always: assumptions and conditions, formulate your hypotheses, calculate your test statistic, find your p-value, and report your conclusion. Our assumptions and conditions. First one, what we always need is randomization, or at least a sample that avoids bias. Our magic number, because we're dealing with means, is 30, unless the data is normal. If the data is normal, any sample size will suffice. Otherwise, we need at least 30, but we do need it from both populations. If we were doing shoes broken down by gender, we would need at least 30 males and at least 30 females, because that data was not normal. The last two are just kind of trivial. I mean, they just kind of have to be true to even consider doing something like this. We do need 2 distinct populations, and we need a quantitative variable. Cannot find the average of a categorical variable. Step 2, formulate your hypotheses. Our null hypothesis is always our parameter of interest equals some null value. And our parameter of interest, the difference between 2 population means, is mu1 minus mu2. So we have the mean from population 1 minus the mean from population 2. And then for purposes of this class, and most of the time outside of this class, our null value will be 0. Well, if our difference is 0, that means that they are equal. So how I like to write my hypotheses here in Chapter 6 is mu1 equals mu2. Or you could say there is no difference between the two population means. Our alternative hypothesis will be one of these three, depending on the question being asked. Either mu1 is not equal to mu2, or mu1 is less than mu2, or mu1 is greater than mu2. Usual caveats, you can use greater than or equal to, or less than or equal to, if you want. I just like using equals. Step 3, calculate our test statistic. It's a t-statistic. It's a hypothesis test on means. This whole thing is called a two-sample t-test. And how we calculate our test statistic, once again, is sample estimate minus the null value divided by the null standard error. Our sample estimate, our best guess for mu1 minus mu2, if we only have sample data, is x1 bar minus x2 bar. Our best guess for the difference between our two population means is the difference between our two sample means. Our null standard error, you can see right here, the square root of s1 squared over n1 plus s2 squared over n2. Step 4, find your p-value. Because we're dealing with means, because we're calculating a t-statistic, we do have to find degrees of freedom. And when we are doing this by hand, we will be super conservative, and we will take the smaller of the two sample sizes and subtract 1. But other than that, we use the same table that we used back in Chapter 3. You find your test statistic along the left-hand side, find your degrees of freedom along the top, find where those meet. If it is a two-sided alternative hypothesis, you pull the value right off the table. If it's one side, you do have to divide by 2. Step 5, report your conclusion. This is always the same. Always compare your p-value to 0.05. If the p-value is less than 0.05, we reject the null and accept the alternative. If the p-value is greater than or equal to 0.05, we fail to reject the null and we fail to accept the alternative. So we will perform a hypothesis test to determine if the average hours of sleep per night is different between all employed students and all unemployed students. Here we have the sample mean, the sample standard deviation, and the sample size for each one of our groups. These are all things that we can find from the Explore option. So just like we did back in Chapter 3, where we were trying to find the sample mean, the sample standard deviation, and the sample size, we can do that broken down by a group. And here the group is whether or not the student has a job. Are the conditions met? Yes, they are. Doesn't matter if the data is normally distributed. Both 71 and 48 are at least 30. We'll assume that it's random enough. There's nothing here that suggests that it isn't random or that there's a ton of bias we need to worry about. We do have a quantitative variable, that being average hours of sleep, and we have two distinct populations, so all of our conditions are met. Our hypotheses, our null hypothesis, mu1 equals mu2. There's no difference between average hours of sleep between all employed students and all unemployed students. Our alternative hypothesis, mu1 does not equal mu2, or there is a difference between the average hours of sleep among all employed students and all unemployed students. Calculating our test statistic, our sample estimate, the difference between our sample means is negative 0.73. Our null standard error, 0.967 squared over 71 plus 0.938 squared over 48 equals 0.1775. Make sure you can come up with these numbers. And then our test statistic is negative 4.11. In order to use the table, we do have to take the absolute value. So 4.11, I believe we have to round down to 4. We use 47 degrees of freedom because the smaller of our two sample sizes is 48. We round down on our degrees of freedom as well. Find where our test statistic and our degrees of freedom meet, and our p-value is less than 0.001. This is very, very significant. It is way less than 0.05, so we reject the null and accept the alternative. We have sufficient evidence to suggest that the average hours of sleep for all employed students is different than the average hours of sleep for all unemployed students. Please note, SPSS will perform this hypothesis test for us if we have the data. Our confidence interval for the difference in two population means the assumptions and conditions are the exact same as what we needed for a hypothesis test. Friendly reminder on what our overall basic formula for a confidence interval is: sample estimate plus or minus multiplier times our standard error. Our sample estimate has not changed. Our best guess for mu1 minus mu2, if we only have sample data, is x1 bar minus x2 bar. Because we're dealing with means, we need a t-star multiplier, and our standard error is the exact same as what we used in our hypothesis test. So our basic formula for a confidence interval on the difference between two population means is x1 bar minus x2 bar plus or minus our t-star multiplier times the square root of s1 squared over n1 plus s2 squared over n2. Using the same information that we used in the previous section, let's find a 95% confidence interval for the difference in hours of sleep per night between all employed students and all unemployed students. X1 bar is 7.08, X2 bar is 7.81, S1 0.967, S2 0.938, N1 71, N2 48. And again, all of this information can be found from the Explore option. Our T-star multiplier for 95% confidence interval using 47 degrees of freedom is 2.021. Our standard error is the same as what it was up above, 0.1775. We plug all this in, and our confidence interval goes from negative 1.09 hours to negative 0.37 hours. Interpreting the confidence interval, I'm blank confident that blank is between blank and blank. I am 95% confident that the difference between the average amount of sleep among all employed students and all unemployed students is between negative 1.09 and negative 0.37 hours. Or, if that's too many words for you, I'm 95% confident that mu sub 1 minus mu sub 2 is between negative 1.09 and negative 0.37 hours. Just like we did back in Chapter 4, we can check to see once if there's a statistical difference based off of our confidence interval. Check to see once if 0 is in our confidence interval. It is not. Both numbers are negative, so 0 is not in our confidence interval, so there is a statistical difference. And our conclusions do match. Both cases, whether we're doing a hypothesis test or a confidence interval, we have sufficient evidence to prove that the population means are different. Essentially, if you don't have to work while going to school, statistically speaking, on average, you are able to get more sleep than those that do have to work. If you do not have to work, you should count your blessings, because you just have more time for everything else, including sleep, including hanging out with friends, and all that stuff. So count your blessings. And please note, SPSS will do this confidence interval for us if we have the data. It will do the hypothesis test for us, and Lab 7 will go over how to do both of those things.